In this series of videos, we're going to review some of the derivative rules that we learned last year. So remember that these are rules that you need to have memorized. Now, it's been a long summer, long extended spring break since we've had to use these. So you might need to make some new flashcards or dig out your flashcards from last year. But I think you'll be surprised with how quickly they come back to you as you work with them. So don't forget what we've got. We've got our general differentiation rules like the power rule, the sum or difference, the constant multiplier. We have our product rule and our quotient rule, which we'll practice. We have the trig rules, and we've got the chain rules. So those are the things that we're going to kind of practice in these next couple of videos to refresh our memory on those. We have also learned the derivative rules for natural log and natural base, meaning e to the x expressions. So we're going to just jump right in. I'm pretty sure we've got the power rule down. So we're going to jump right in with the product rule and the quotient rule. So we want to take the derivative of f of x equals 2x squared times the sine of x. So I'm going to choose to split this. So I'm looking at my product as 2x squared times sine of x. So this is what I'm going to call f, and this is what I'm going to call g. So remember that the product rule, in order for us to find this derivative, f prime of x is going to be f prime g plus g prime f. That's our product rule. So here we go. The derivative of f, 2x squared, is going to be 4x, and then we leave g alone, sine of x, plus g prime. So remember when we do trig derivatives, the co's come out negative. So this is just regular sine. So the derivative of sine is going to be cosine, and we keep f the same. So this is going to be 2x squared cosine of x. And we can't really do much else. We could do some factoring, but again, the question is always, do we need to? And in this case, no, we don't really need to do anything else. We just wanted this derivative, so here we go, f prime of x. That's a refresher of your product rule. Let's do a refresher of our quotient rule. So if we look at number 2, we have this rational expression here. The derivative rule for a quotient, in this case, g prime of x is going to be equal to f prime g minus g prime f all over g squared. And so the way this works is that f is our numerator, g is our denominator. So that's what we're going to work with. And then we'll try to simplify as much as we possibly can. So here we go. F prime g, the derivative of the numerator is going to be 2x plus 5, that's the end of that, times g left alone, which is x squared minus 4, minus g prime, so the derivative of x squared minus 4 is 2x times the numerator left alone, x squared plus 5x plus 6, all over g squared, which is going to be x squared minus 4 squared. Now, I want to try to simplify that on the top. I could multiply it out and see what happens there. But what I'm actually going to do first, and there's more than one right way to do this, but I'm going to consider the fact that this is x plus 2, x minus 2, and that this one factors to x plus 2, x plus 3. And because what that shows me is that I have an x plus 2 in common that I can factor out. The denominator is also factorable to x plus 2 squared, x minus 2 squared. This is x plus 2, x minus 2, and then when I square that, I square each of the factors. So you can see when we simplify here, we're going to be able to cancel out a factor if we do it that way. We're getting into some fancy algebra here now, which is what calculus is all about. So I'm going to factor out that x plus 2. That leaves me with 2x plus 5 times x minus 2 minus 2x times x plus 3. Now, you could have chosen not to do that. You may not have been able to see that that factor was something in common at the end, though. So that might not have been the most helpful, but I think it would have been fine not to. So now we can see that one of these is going to divide out the x plus 2. Up on the top, we're going to have to do a little more work to get this simplified well. So I'm going to FOIL and distribute in the numerator so that I can combine like terms. Here's what that's going to look like. Multiply out those first two binomials, distribute out the negative 2x. That's what we get. I could multiply out the denominator, but that's usually not, going to be super useful. So we might as well leave it factored. And then we can go ahead and simplify that down with like terms in the top. And this is what we end up with when all is said and done. Now, the reason why factoring that x plus 2 out at the beginning is nice, because you may not have ended up with something that appeared factorable at the end. You probably would have had a quadratic there that would have had that factor of x plus 2 that then you could factor out. So it's kind of like pay me now or pay me later. It's going to happen one way or the other. So that's kind of a messy example with a lot of simplifying happening. But again, the general idea of how to use the quotient rule is really this beginning step right here. Once you can get that part, the rest is just kind of simplifying. All right, let's look at example 3. This is just kind of a reminder of some of the things that we can do with derivatives. This is review of things that we did last year. We want to find the equation of the tangent line to the equation f of x is equal to sine of x over x squared at x equals 0. So we need to know two things here to make that work. We are going to need the slope at x equals 0, which means we need, I'm still on a highlighter. We need f prime at 0. And then we need an ordered pair, which means we're also going to need f of 0 so that we can make our ordered pair xy. So this is a quotient, and we're going to need to use the quotient rule. So to find our derivative, f prime of x, derivative of the top is going to be cosine of x times the bottom left alone minus derivative of the bottom times the top left alone over x squared squared, which is going to be x to the 4th. And we can clean that up, but we really don't care about having the derivative nice because we just need that value f of 0 and f prime of 0. So f prime of 0 is going to be cosine of 0 times 0 squared minus 2 times 0. I forgot. This is a typo. This isn't going to work at x equals 0. It's going to be undefined there. So we won't have a tangent line because we're going to end up over 0 to the 4th. So I had meant for this to be changed to x equals pi. That works out a little bit nicer. So let's make that little adjustment right here. So instead, let's plug in, instead of 0, let's do f prime of pi so that we don't have that undefined error. So we have the cosine of pi times pi squared minus 2 pi times the sine of pi over pi to the 4th. Cosine of pi is -1, so this is negative pi squared. The sine of pi is 0, so this whole thing drops out, over pi to the 4th, which simplifies to -1 over pi squared. That's our slope. Okay, so that's f prime at 0 at pi, -1 over pi squared. And then similarly, we'll change this value to pi. So f of pi is going to give us our ordered pair. So f of pi is going to be the original sine of pi over pi squared. Well, the sine of pi, again, is 0, so this whole thing is 0. So that means the ordered pair we want to use is pi 0. We need all of that because, again, what the question is asking us is to find the equation of the tangent line. So we can use our point slope equation, y minus y1 equals m times x minus x1. And all we got to do is plug in that information. So our ordered pair is pi 0. So that's going to be y minus 0, which is just y, equals negative 1 over pi squared times x minus pi, and we can leave it just like that. So there we go. That is our tangent line. Okay, now the last thing before we end this first video is if you look at the next question, and we're going to have to adjust this too since we changed from 0. What we want to do on the next question, it says use your result from number 3 to approximate the value of, in this case, the value that we want to approximate is, let's do f of 3.1. So let's change this. We want to approximate f of 3.1, okay? So that just means we're going to use that tangent line, which was y equals negative 1 over pi halves times x minus pi. We want to evaluate that when x is 3.1. So let's plug that in. We have negative 1 over pi squared times 3.1 minus pi. And let's go ahead and put that into our calculators. It gives the answer in scientific notation. So it's going to be 0.00421 is what we get there. Now this is an approximation to f of 3.1. Remember, the original function for f of x was, I think, sine of x over x squared. So let's use our calculator and figure out what the actual approximation using the calculator, whoops, that's not what I meant to put in there, is for f of 3.1. And see how decent of an approximation that is. This value comes out to 0.00432. So it's a pretty close approximation on that tangent line. Remember, whatever our graph is doing, the tangent line is something like this. So what we're doing is we're using the equation of the line to maybe find if this is, remember, at pi, 3.1 might be just slightly off to the side of that on the tangent line. So is it exactly equal to the function? No. The question is then, would this still be a good approximation if I were to use, right now I used a number like 3.1. What if I used a number like 5? Would that tangent line still be a good approximation for 5? Well, the further we go out, the more distance there is between the tangent line and that curve. So we can see that the approximation is only good or close at areas very, very close to that point of tangency. This idea is called local linearization, and that is something that we'll discuss quite a bit more in this class that we haven't before. So that is a quick review of the product rule and the quotient rule, and in the next video, we will refresh over the chain rule.